Hello. If you've taken a calculus class, I'm sure you've discussed the absolute value function, specifically f of x equals the absolute value of x at x equals 0. And at x equals 0, it has that kind of peculiar behavior, right, where it's continuous, yet it's not differentiable. And that may seem a little bit weird to you. So today, we're going to discuss that. Hello, welcome back to the Quant Plus YouTube channel. As we said at the beginning of the video, and I hope your calculus teacher drilled this into your head, the function f of x equals absolute value of x is continuous at x equals 0, but not differentiable at x equals 0. And so today, I want to give you a semi-formal proof of this and a more formal version or explanation for why this holds. We're going to start off by considering the limit definition of the derivative, right? So in general, the limit definition of the derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x over h. If we consider the absolute value of x at x equals 0, then we get to the following. The f prime of 0 is the limit as h approaches 0 of f of 0 plus h minus f of 0 over h, which in turn becomes the limit as h approaches 0 of the absolute value of 0 plus h minus 0 over h. And this then simplifies a little bit to the limit as h approaches 0 of the absolute value of h over h. And here I'm going to remind you of a very important fact. If the limit as x approaches some value c of f of x exists, then the limit as x approaches c from the left of f of x exists, and the limit as x approaches c from the right of f of x exists, and they equal each other. And so applying this concept here, our limit as h approaches 0 of absolute value of h over h has to exist as two independent one-sided limits. Well, let's consider the limit as h approaches 0 from the left of absolute value of h over h. Well, considering a slightly negative value, right, slightly to the left of h equals 0, the absolute value of that term will still be positive, but because we have a negative term, we're dividing by negative, and we have positive over negative, and this becomes negative 1. If we now consider the limit as h approaches 0 from the right of absolute value of h over h, well, if h is positive, then we don't really care about the absolute value, right? Because the absolute value takes negative terms and makes them positive by essentially considering what the distance is from 0. And this one-sided limit is equal to 1. But we know that negative 1 does not equal 1. And from here, we can conclude that the limit as h approaches 0 of absolute value of h over h does not exist. Well, if this limit doesn't exist, and our derivative function is defined in terms of this limit, this is why, or one explanation for why our function absolute value of x is not differentiable at x equals 0, despite it being continuous. And a more formal version of essentially the same thing is as follows. We're going to consider the epsilon delta definition of the derivative, right, which is stated as follows. The limit as x approaches c of some f of x is equal to L if for any epsilon greater than 0, there exists a delta greater than 0 such that if the distance between x and c, which I'm going to write as the absolute value of x minus c, is less than delta, then the distance between f of x and L has to be less than epsilon. And well, this looks a little bit abstract, but the intuitive explanation for what the epsilon delta definition of the derivative is saying is that if our x value is close enough to c, right, within the same neighborhood, then our function value, f of x, has to be within a specified neighborhood of L, right, our proposed limit value. In a real world example, if everyone in your town, or most everyone in your town who graduated high school went on to university, then you are very likely to go to university, right? So pretty much if you are coming from a similar background to someone, then you're likely to have similar future endeavors as someone, right? That's the kind of like maybe the real world application of what the epsilon delta definition of the derivative is saying. Well, if we then apply this formal definition, right, to our same limit definition of the derivative, well, our limit definition of the derivative is, once again, this. And we said earlier that this ends up being the limit as h approaches 0 of absolute value of h over h. Well, now kind of giving us this formal framework, if we go the smallest possible amount in the positive direction, right, then this will go to positive 1 for even the slightest positive value. And this will go to negative 1 for the slightest negative value, which means that we can find a value of x that's arbitrarily close to 0, yet the limit value is enormously different, right? It goes from 1 to negative 1. And so I'm not writing out the formal steps, but by employing this argument, the intuitive argument is that x can be arbitrarily close to 0, yet our limit can jump from negative 1 to 1, even if we're very, very, very close to 0, arbitrarily close to 0. And this is the formal argument for why the absolute value function is not differentiable at x equals 0, even though it is continuous. So, if you found this content informative, please consider supporting the channel. You can do that by liking this video, sharing this video with your family and friends, subscribing to the channel, and if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.